Everyone, welcome to the HR MacMillan Space Centre. It is Thursday. It is 2 o'clock. You know what that means. It's time for our weekly chats with our astronomer, Rachel. Hey, Rachel, how's it going?
Good. It's sweltering hot today. Oh my goodness.
It sure is. This is why I have now transitioned most of my work outside of my kitchen, which is also sweltering hot. It's south facing, so it just gets so hot in there. It's nice and cool here in the Space Center. But there was some exciting stuff that was happening this morning. We finally had the launch of the Mars 2020 mission. Has the Perseverance rover as well as a bunch of really cool instruments on there. How are you feeling about this mission?
Really excited. Curiosity was my favorite rover to go to Mars, mostly because it landed on Mars on my birthday.
Okay.
But I'm excited that Perseverance is kind of following on the legacy of Curiosity and kind of extending it further, much like James Webb is doing for Hubble. So what it's going to find, I have no idea, but I'm excited to see it.
And this is quite close to your birthday as well. So you'll have some competing, landed on your birthday, launched near your birthday. But Perseverance is probably going to be discovering some cool things, including that helicopter. I mean, like we had a whole series, our Cosmic Night, a few weeks ago with Joelda Moranzi from the University of Chicago. So for any of you out there that weren't with us for that Cosmic Night, we're going to be posting that on our YouTube. You should definitely check that out. Full hour programming with Rachel and Joelda, just nerding out about Mars because there have been a few launches because NASA has sent the Perseverance rover up there. The UAE launched their mission up to Mars as well, and there's a reason for this. Like we kind of talked about this, but all of these missions have launched around the same time, and they're all going to arrive at the same time as well. It means that February is going to be a busy time at Mars. Could you maybe explain why that is?
Yeah, so it does take 7 months to get there, and it'll be really exciting to see when they arrive to be able to see all these science and technology demonstrations because, Mars is this faraway planet and there's still so many things to be discovered on Mars. And what I'm particularly excited for actually is you mentioned Ingenuity, the helicopter that's going there.
Yeah.
It would be the first test of a powered flight on a totally different planet. And we're hoping that it'll fly for a segment of 90 seconds, which is no small feat because the Wright brothers, I think when they had their first flight was only around 10, 12 seconds long. So we're really shooting for a high bar here.
And I'm really excited that there's going to be all these robots. There's now going to be a planet that can probably say that it's predominantly actually all just dominated by robots orbiting around and driving around on the surface. I think that's kind of cool.
It's cool. So maybe we shouldn't be worried about robots taking over Earth, but robots taking over Mars instead.
Pretty much, they're going to form a democracy.
Yeah.
They're going to have a government. That Curiosity is going to be the ruler of Mars. I think there's a sci-fi story in there somewhere. So this week, Rachel, of course, we've gone through all of our Mars stuff, and now we're getting into the heat of the summer here. So we thought we'd take a look at the sun. And of course, the sun produces light. So we're going to delve into this theme of light and what it is. And of course, that may open up a few other topics. And for any of you out there on YouTube land, of course, all of you out there on Telos Optic as well, hopefully you'll be able to join us on our YouTube channel. Please put your questions, comments into the YouTube chat box, and we're going to get through all your questions. We're going to get into light, and of course, if you want to talk about Mars Perseverance, we'll talk about that too until we get to 2:30. So let's get going. We'll hand it over to you, Rachel, for a quick little presentation on light.
Sure, thank you. So you should be able to see the first slide that says light on it, and
just not quite yet. There it is.
There we go. So electromagnetic radiation is one of the many ways that energy travels through space. So there's things like X-rays when you go to the doctors, the energy used to cook food in your microwave, and light from the sun are all forms of electromagnetic radiation. Now, electromagnetic waves consist of two waves that oscillate perpendicular to each other. So one is a magnetic field, and you see that in red here, and the other is an electric field shown here in blue. Now we can classify these waves according to their wavelengths or their frequencies, and we call this the electromagnetic spectrum. So here we can see that visible light, or the light that our eyes can see, is really just a tiny portion of all the different types of radiation that can exist. And we see on the right-hand side here, blue or violet light has more energy because it has a shorter wavelength. So we're really packing more punch over a shorter distance. And by contrast, we look all the way on the other side, we have red light, which has a longer wavelength and therefore less energy. And to the right of the visible spectrum, we see more energetic forms of radiation that are harmful to living organisms. So this is why we wear sunscreen at the beach, or why X-ray technicians place a lead shield over your body. And fortunately for us, our atmosphere absorbs gamma rays. Now to the left of the visible spectrum, we have lower energy radiation, which is not harmful to us and actually surrounds us constantly. We also know that light travels in materials at different speeds. Physicists have a number, it's called the refractive index, that describes how fast light travels through a material. A higher refractive index means a slower speed of light in a material. So to explain how this works, let's imagine that you are a light beam. You are walking on the sidewalk and suddenly you happen upon a stretch of mud. Now, as you approach, you're coming on an angle, which means that your left foot steps into the mud first. So that means that your left foot is slowed down, but your right foot is still going at the same speed. So that means that you end up turning just a little bit. Then when your right foot catches up, it's now in the mud as well. So therefore, both your feet are moving at the same speed and you continue going in the same direction. So that really is light being slowed down, almost like your feet being slowed down in mud. So now the history of light. Newton thought that light was made out of particles and he called them corpuscles, and other scientists thought this as well. We know that light is made of particles because we can take a very sensitive instrument that makes clicks when the light shines on it. And if the light gets dimmer, the clicks are the same loudness, but there are just fewer of them. So light is almost like raindrops, and each droplet or lump of light is called a photon. But then in 1801, a guy named Thomas Young demonstrated that light passing through two slits add together or cancel each other. We call that constructive or destructive interference. And then we saw that these interference fringes, or these patterns, appeared. Now, this phenomenon can't be explained unless light is considered a wave. So we have kind of a photon self-identity problem going on here. So here's a short video showing this experiment that Thomas Young did. And to the right, we have the results of the experiment. So you'll see that it pops up on the screen on the back over here. So here we have light being treated as a particle. We're firing particles through this double slit, and they end up on the screen, just as you would imagine, kind of all over the place. And now we're switching to light being treated as a wave. Now it's going to pass through the two slits, and we're going to see something interesting here. We're going to see interference happening. So that constructive and destructive adding and canceling that we talked about before. And now we see this fringe pattern happening here, like you see on the right-hand side. So this problem, this apparent duality between light being a wave or light being a particle, was actually solved in the mid-1920s with the advent of the correct equations for quantum mechanics. Now, I won't dive into the theory behind that, but if you're curious, you can actually go to our website and look at my blog post. Right here is the link, and other blog posts for each themed week written by different members of our staff. Now, I want to talk about recent advancements in light, in particular, laser physics. So you probably heard about the name of Donna Strickland, who was the 2018 Nobel laureate for physics for her work on something called chirped pulse amplification. And I'll give you a simplified rundown of how it works. So at the University of Rochester, at the Laboratory for Laser Energetics where she worked, they had two major lasers, one that could produce short pulses of light and another that could produce high intensity light. But researchers weren't able to combine the two without damaging the laser. So this is where the Nobel Prize winning idea comes in. The goal is to have a lot of energy and a very short pulse, but we don't want it in the amplifier for fear of damaging very expensive laser equipment. So how do we avoid this? Well, there's a few different things we can do. So we start with pulse stretching. So to explain this, I'm going to borrow a few of Donna's slides here. So remember we said that red light has the least amount of energy. So when they meet up with atoms in a material, they don't really interact and they just pass on by. They travel faster than the green photons, and the blue photons take a little bit longer to decide if they want to exchange energy with the atom, so they travel the slowest. So if these photons travel down a 1.4 kilometer long fiber, we'll see that they end up spreading out quite a bit by the time they reach the end. Okay, so to get a long pulse, we want to send in the red photons first, then the green, and then the blue. And now we've got to amplify it. So we have some material, or what we call a laser rod, shown here on the left, with some red atoms over here that are excited and given some energy by some energy source. So then we send in a photon, this little red guy over here, and it meets an atom. It says hello, and then it takes that atom's energy, creating 2 photons. These 2 photons meet 2 more atoms and create 4 photons. And these 4 photons are created having only given up 2 atoms of energy. And then those photons will go on to create 8 photons, giving up 4 more atoms of energy. Now you can see that this process is really wasteful because we leave most of the energy behind in the amplifier, behind all these atoms that didn't interact with the photons. So this is why we have to keep building larger and larger lasers if we want a lot of energy. All right, so now we have a long pulse and we've made it a little bit bigger, we've amplified it, and now it's time to compress it in a short space. So we use a set of parallel gratings. They act kind of like prisms and they send different colors of light out at different angles. So because we stretched our pulse, here we have the red entering first, the red photon actually travels a bit further than the blue photon here. And by the time the blue photon hits the second grating, the red photon would have traveled this longer distance and they arrive at the same time. So all the photons are put back together and we have a short pulse. So here's an overview of chirped pulse amplification, or CPA for short. So we stretch the pulse by sending light down a really, really long fiber. So then we end up having a long pulse with low energy. And now we want to amplify it. So we want to give it more energy. And we do that by allowing photons to steal energy from excited atoms, creating more photons. And then finally, we want to compress it using gratings that send colors of light at different angles, creating this short pulse. Now, I think it's interesting. The question is, why is it called chirped pulse amplification? And it's because a bird's chirp is called a chirp because the sound frequency changes in time as the bird sings a note, just like different colors or frequencies of light are used to our advantage here in CPA. Now, CPA is exciting because it is the current state-of-art technique used by the most highest power lasers in the world. And we see that there's a little bit of a plateau over here right before the invention of CPA. And that's because there were many methods developed for emitting extremely powerful short laser pulses, but then development stopped because it wasn't possible to amplify the light pulses further without damaging the amplifying material, damaging the laser itself. But with the invention of CPA, we can actually attain those higher orders of magnitude and peak power in laser systems than ever before. And we use this high energy regime to be able to probe high energy physics and study it. And so that brings me to the end, and Michael, will throw it back to you to talk a little bit more about light and perhaps the Perseverance rover going to Mars.
Awesome, Rachel. Yeah, certainly gives us a lot to think about these summer months as the heat and light is hitting us during the summertime. And one of the things that the connection that you talked about, Rachel, is the radiation as well. So could you talk a little bit about sort of like how the light from the sun and the radiation are also like impacting us? Of course, like the light is hitting us, we can see, but where does the radiation come in?
Right. So light really is on the spectrum. So it's electromagnetic radiation. So when we normally talk about light colloquially, we're really talking about visible light. So the light that we can see with our eyes because everything else is invisible to us. Right. But if you have something like an infrared camera, you're looking at infrared radiation, which is still light. It's just invisible to us, but a camera can see it because we've programmed it to look at those wavelengths or those frequencies of light. And so with the sun, we have ultraviolet radiation. It's quite energetic. It has a short frequency, so that means a lot more energy packed in a shorter distance. And that's why we need to wear a sunscreen, especially on days like today.
Right. And I think that's a really important point because when we're talking about light, and I guess when most of humans are talking about light, we are talking about the visible spectrum. But of course, we could also think of it like perhaps there are other creatures and there are creatures on this planet that can see beyond what's the visible spectrum, right? Yeah,
and I think reindeer are an example of animal that can see in ultraviolet, which is kind of weird.
Yeah, I heard a really funny fact the other day. So moles, so the fact was moles shine in all colors of the rainbow, yet can't see any of it. And that's because moles are basically blind because they burrow under the ground, but they also have this like oily sheen on them that when the light hits it, it sort of refracts, and creates that nice rainbow. So they look very pretty if anyone sees them sort of like shining in the light, but they're basically blind, so they have no idea that they shine like a rainbow.
Oh, that's so sad.
Yeah, so let's get into light. And of course, if anyone out there on YouTube land wants to ask any questions about light or anything about Mars, we'll just keep going and talking about light. Let's talk about some of the other things that are on the electromagnetic spectrum. So light, of course, doesn't really give us do we use light in any way to give us energy? Do we harness it at all? Like when we're talking about solar power, is that from the light?
So solar power is really interesting because it comes from actually what Einstein won his Nobel Prize for, and that's something called the photoelectric effect. And he found that if you shine light on a metal, you can actually have the light impart energy onto atoms in the metal and then knock off some of these particles. And so that's essentially what these solar panels are doing, right? So they accept light, they accept photons. These photons are knocking off little bits of particles. Those particles or electrons are really generating a current, because a current is really just a movement of electrons in a stream. So we do harness energy. We don't quite do it the same way that solar panels do or plants do with photosynthesis, yeah. But us being humans, being very creative, we've come up with the technology to do it for us.
Yeah, and of course, lots of people say that it's healthy to go outside because you're getting vitamin D. Now, where does that come in? Because I know that there's a lot of conflicting information. Of course, go outside, and of course, the radiation from the sun is going to be harmful to your skin, but it also produces, a vitamin that's very important for us. So, do you know anything about what's happening inside of our bodies to produce that?
I actually don't, but that's a really interesting question, because that makes me think of when you talked about whether or not we can harness energy from the sun. And I really do feel like I feel a little bit different if I spend all day in my dark sub basement and never going outside. I need to go outside and soak up that vitamin D. But that's a really interesting question. I'll have to think a little bit more about that.
Yeah, maybe we'll come back to that maybe next week. So, because I'm thinking about, there's always a trade-off, right? Like there's nothing that's like 100%. I think, like, of course, going outside, especially during a pandemic, is healthy for us. But during really long summer days, that radiation is going to be quite harmful. So there's always kind of like, I think, a balance, and I think moderation is good for everything. Let's go
moderation.
One more question that I do want to get into, maybe we sort of spark some ideas about what light and what the sun can do for us, because there's this new idea of spacecraft using light, and it's called solar sailing. Could you maybe tell us a little bit about how solar sailing works?
Sure. So I think solar sails are this really crazy idea that only works in space, because space is quite close to a vacuum. And the reason I say it's crazy is because we're really using light from the sun, or photons from the sun, to push a spacecraft. And you're thinking that, okay, well, we just sent the rover up to Mars. We used a massive rocket with a lot of fuel and a lot of power to send that into space. But then we think about the solar sails, and these solar sails only get pushed by photons. And so it's really comes down to conservation of momentum. So you have photons, these particles, hitting the solar sail. They impart a momentum that pushes the solar sail one way, and the photons get pushed the other way. So it's really kind of hard to imagine the amount of power you can get from these quanta of light, or these photons, but it really does work.
And it's a lot cheaper too, because you can just get this free energy from the sun. What a nice, generous offer the sun is giving us, because fuel is quite expensive. And I think, like, for the purposes of what solar sailing can do, and obviously what the Planetary Society has proven with light sail, that they're able to orbit around our planet basically with free energy, using the solar sailing technique. And so that opens up a lot of possibilities as more countries and even private companies go up into space to start to think about how they could possibly use solar sail technology. I think that's really fascinating.
That's a good point, because fuel costs a lot to use and also send up into space. It's quite heavy. So you do actually have that balance between how much fuel do I need to lift off all these kilograms of material and how much does that fuel weigh. So if we could harness the free energy of the sun, I think that would be fantastic.
And you can say that you're surfing on the sun. I mean, that's just a cool thing to say. Let's go to some questions now on YouTube. And Harry's with us most weeks. Hey, Harry. He's got the first question this week. He asks, how is light speed calculated, and is it really constant? So maybe just talk about a bit about the speed of light, and maybe talk about how it's calculated.
Ooh, okay. So to my knowledge, the speed of light is this fundamental constant. And I think that it's measured by using or timing how fast light travels from one end of a meter stick to the other and how long that takes. And so that's how we get that unit of measurement for meters. And I think that the same thing goes for deriving the fundamental constant of light. But I also feel like there's another way that we can do it as well. But it's not coming to my brain right now.
Yeah. So his other question was, is it constant? So that was sort of like something that, of course, in a lot of your calculations, it's nice to have a constant, because if you have some variables that may mess out some calculations. So is the speed of light actually constant?
It is. And that was one of the beautiful parts that came out of Einstein's special relativity, is that no matter what frame you're in, there's no preferred reference frame or reference frame that you're looking at the laws of physics in. And anyone that looks at light will always agree that light travels at, this insanely fast speed, the fastest speed that we have, or this cosmic speed limit. And actually, it just came back to me how we can derive the speed of light. I was going through one of my courses on electromagnetic theory, and it's from someone called James Clerk Maxwell, and he gave rise to the Maxwell equations. Now, these govern how electric fields and magnetic fields propagate through space, and it governs their properties. And one of the things that falls out of these equations, or these sets of equations, is the speed of light.
Just reminded me, I think there was an episode of the new Cosmos that there was like an animated sequence that showed how Maxwell did some experiments. If I recall, did you watch the new Cosmos?
I did not.
I believe anyone out there, there were a little animated sequence, and they were doing like these experiments with these lanterns on a beach. I'd have to look that up, but I think that was sort of like his early experiments with trying to, I think, time the speed of light. Let's go on to a really good question. I like this one from AD300. Are there other sources of light in space other than the stars and the sun?
Ooh, that's a very good question. And it's a really good example of light coming from something that isn't a star. And that would be the cosmic microwave background, actually. Yeah. So the CMB right now is in the microwave wavelengths, and it has a temperature of around 2.73 Kelvin. So it's quite cold. It's very close to absolute zero. And the reason why I use this as an example is because the CMB are remnant photons from our early universe that took a really long time, 14 billion years, to propagate through space and eventually get stretched out into these microwave wavelengths. So we actually do see remnants of photons or remnants of light that aren't generated by stars. And we see this as the cosmic microwave background.
And of course, I was just thinking of like there's like those fireflies that create light. And I always kind of like wonder, like, what if there was like some form of life? So if there is some life on this planet that actually produces light, could there possibly be like a more advanced, perhaps bigger forms of life, perhaps even like trees or something like that? It starts to like let my sci-fi brain wander about the possibilities of other things producing light.
Yeah, the mind boggles.
Let's go back to some questions here. What are any new promising technologies using some of the other parts of the light spectrum?
Ooh, I would probably say that the one that everyone is talking about is James Webb, and that's because we are hoping that it will be able to peer further back in time than ever before, so even further than Hubble was able to see. And what's particularly interesting about James Webb is that all of its science instruments are covering the infrared part of the spectrum, or the near infrared part of the spectrum. And the reason that is because there's a lot of stuff in space. There's a lot of dust, gas that gets in the way of us trying to see things that are further. So with infrared, because dust doesn't emit any heat, doesn't emit any light, so we can look right through these dust clouds and see further beyond.
Yeah, of course, like it just got delayed again, unfortunately. This wonderful new telescope, once it gets up there, it's going to be amazing. We keep pumping it up. It's going to get up there eventually. But when I think back to, and I wasn't really, thinking about the Hubble Space Telescope before, because it was like that was a bit more before my time, but it did have its early kind of like struggles even after it got launched into space. So maybe this is just sort of like par for the course for these big telescopes. We just have to be patient. Eventually it's going to be up there and it's going to be amazing. But one thing I just want to follow up on, Rachel, that you brought up a good point, which another question that came in from Pride, which is light and heat. And those are two different things, but also kind of like also connected in, I mentioned before about radiation. So maybe bring in heat into the equation and where that comes from as part of this light spectrum that we're talking about.
Sure. So heat is really, it is infrared radiation. They really are the same thing. And you can imagine that when I say you have a thermal camera or an infrared camera, I'm really talking about the same thing, because both of these cameras will show you red being hotter spots and blue being colder spots. But we tend to think that heat is a separate definition from infrared because we don't often think about other wavelengths of light besides the visible light or visible part of the spectrum. And so when we say heat, it really is equivalent to infrared light, which is a little bit bizarre to think about.
So when we're feeling the heat, that is when we should be more concerned about the radiation. Is that what you're saying?
Yeah, so that you would be really hot on an infrared camera.
But and I guess this brings up a good point, because in the wintertime, and I'm not much of a skier myself, but I do know people that go up skiing, and they often get sunburns on their faces, and of course it's not very hot up there. So where is that coming from? Because obviously there's a lot of light being reflected off of the snow, and they're getting a lot of, obviously they're being burnt on their face. Is there an explanation for that?
So my best guess is probably what you're talking about, referencing snow blindness. So because snow is highly reflective, it's almost like the same concept as the moon having that white dust covering its surface. Same thing happening here with snow being white and very, very reflective. It reflects sunlight into the eyes of people skiing, which is why they wear goggles. So I think the same kind of thing is happening here, where light is being redirected. Instead of going down, it's going down, bouncing off, and then going directly into their faces.
Yeah, so that's another thing that I don't get up to either. I sound like really boring. I know I don't like going to the beach. I don't like going up on the mountains. Why am I living here in Vancouver? I'm just talking out loud now. I do have fun. I'm going to go out and play soccer a little bit later. So once again, this brings us to pretty much to the close. If anyone wants to add a last minute question to get in here, of course, every week we get into another theme. Next week we're going to sort of like take light and do a little bit of a spin on it, because we're talking about light pollution next week. And Rachel, you're not going to be joining us because, of course, that aforementioned birthday of yours. But I'll be here talking about light pollution, which is actually a near and dear subject to my heart, which will then lead to a couple weeks, the Perseid meteor shower. And we are going to be doing an event here in person at the Space Center, of course, all outside. Our observatory is going to be open, but Rachel and I are going to be outside in the field as well. And we're going to have a loudspeaker on, and this will be at night. The venue park, of course, not being the best location that you could go to, but it is a not bad location if you stay out there long enough and can dark adapt, we're certainly going to be talking about what we can see up there in the nighttime sky. And we'd really love to see all of you down supporting us. Of course, we love your support joining here on our 2 p.m. YouTubes. If you'd like to donate to us, you can go onto our website and click the Donate Now button. And as Rachel mentioned in her presentations, every week we have blogs. We got lots of resources. If you're learning from home, pretty soon we'll be doing school from home and also in person as well. And we're going to be transitioning into those school years as well to support all of you. So we really appreciate your help. So that's it for me, Rachel. Do you have anything more before we sign off?
No, but I'm very excited for the Perseids.
All right. Hopefully see you then.